Hi, welcome back. This video is on power. Okay, so power is how quickly you can get work done. The more power, the more quickly you can get the work done. Less power, less quickly. The work could be the same, and probably is the same, it's just how quickly you can get it done. That's why we would rather drive the souped up Mustang compared to the Smart for 2. You're going to do the same amount of work going from place to place, but you're going to do it a lot more quickly if you're in the Mustang than if you're in the Smart for 2. Okay, so no matter how fast we get up the stairs, our work is the same. We're going the same distance and lifting the same weight. But if you run, it requires more power because you're spending less time. You're doing that work in less amount of time. If you walk upstairs, you're doing the same amount of work as if you had run, but the power demands are less because you're not transferring that energy from the ground floor to the top floor in as short of a time. So average power is calculated by measuring the work over time, the amount of work divided by the time that it took to do that work. In the calculus world, it would be the differential or the derivative of work with respect to time. Or if you know the force you're applying and how fast the object is going, you multiply the two of those together, and that tells you the power. So 3 different formulas to find the power. And now the units of power. So the SI unit for power is the watt. It's named after the engineer James Watt, who perfected the steam engine. Okay, so this was done in the early 1800s. And that's when the Industrial Revolution was beginning, and people like Watt and Joule were working on the topics of energy and energy conversion. In the British system, which we still use a lot, it's the horsepower. It's equivalent, 1 horsepower is equivalent to 746 watts. And that's an old definition based upon how much work a standard draft horse could do in an hour. Now, how do we buy energy? We talk about this here, even though it's really an electrical topic, but at home we purchase energy, and this is how we purchase it. So your power company, and that's really kind of a misnamed company, it should be the energy company, but we call it the power company, and they charge us for how many kilowatt hours we consume. Now, a kilowatt is 1,000 watts of power, and if it's a kilowatt hour, it's 1,000 watts of power used for 1 hour. So it's really energy. If a watt is energy work done per unit time, and then you multiply it by a unit of time, the time units cancel out, and it leaves behind the energy. Okay, so 1 kilowatt is equal to 1,000 watts. 1 hour is 3,600 seconds. 1 kilowatt hour is equal to 1,000 joules per second. Okay, 1,000 joules per second is 1 kilowatt, and times 3,600 seconds, so the seconds cancel out, work per time times time gives us the amount of energy. So 1 kilowatt hour of energy is equivalent to 3.6 times 10 to the 6, or 3,600,000 joules of energy. A lot of energy. So if you use your hair dryer for a whole hour, you will have used over 3 million joules of energy. Now here's your multiple choice. Welcome back. let's do a couple of problems here. So we have a man, he's running up the Empire State Building. There's 1,600 steps, and he does it in 20 minutes. If the height gain of each step was 0.2 meters and the man's mass was 80 kilograms, what was his average power output during the climb? And we want to give our answer in both watts and in horsepower. This problem will help you do one of the labs we're going to do this week. We're going to find out how much horsepower you have. Okay, first thing I'm going to do, I'm going to draw a free body diagram on the man. Okay, the man has that weight, mg, and the steps are applying a normal force. So for the man to travel up at a constant speed, we would say the sum of the forces is equal to 0 is equal to normal minus mg. So the man has to push on the steps with a force equal to his weight, so that the steps in return, according to Newton's third law, will push up on him with the same amount of force. Okay, well, we want to know what the power output is, the average power output. So power is equal to the amount of work done in the period of time. Okay, well, the work is the force times the distance and over the time. Well, we know what the force is. It's the normal force, which is mg. And we know what the distance is. Well, we have to do a little calculation. It's 1,600 steps times the height of each step. So that's going to be 1,600 times 0.2 over the time. Well, it was 20 minutes. And we need to turn this into seconds. So it's 20 minutes at 60 seconds per minute. Okay, so I'm going to plug the numbers in. So 80 times, I'm going to call it 10 just to make my life easier, times 1,600 times 2 over 20 times 60. I want you to confuse that with being squared. 80 times 10 times 1,600 steps times, oh, and that's 0.2 meters. Almost blew that one. Times 0.2 divided by, and I'm going to put parentheses around this, 20 minutes times 60 seconds per minute. Close that parentheses. Come up with our number, and it's 213 watts, or 213.3 watts. That's how much power the man is using as he runs up the stairs. Well, how many horsepower is it? This is a unit conversion. There's 746 watts per 1 horsepower. Okay, so I'm going to need to divide 213 by 746 to come up with the horsepower. And if we look at the units, the watts cancel out, leaving horsepower behind. And let's pull up our handy dandy calculator again. And that's going to be 213 divided by 746 watts per horsepower. And that's about 0.2859, so about 0.29 horsepower. Okay, so that doesn't sound like very much. But you run up the Empire State Building in 20 minutes and see how you feel after that. Okay, next up. Calculate the power output of a 0.1 gram fly as it walks straight up a window pane at 2 centimeters per second. Okay, so this one, we're going to use another variation of power, and I'm going to show you how that comes about. Power is equal to work over time. Okay, and that's equal to force times distance over time. And if you look at just distance over time, That's the same thing as saying force times velocity. Now this has to be an average force times an average velocity unless you're doing the calculus. Okay, so the force on the fly. So believe it or not, it's actually a friction force that allows the fly to climb up the window. Okay, so that means the friction that the force that the fly applies to the window applies to the fly is equal to mg. And we have to remember that this is in grams, so we have to turn that into kilograms. So 0.1 gram, I have to divide that by 1,000. So 0.1 times 10 to the minus 3 times 10. I'm going to use 10 for g. And that gives us how much the fly weighs. And that's the force that the fly is applying, or the window is applying, moving the fly up the window. We also have to turn our speed from centimeters per second into meters per second. So to turn centimeters into meters, we have to divide by 100, so it's 0.02 meters per second. So let's go ahead and now do our calculations. The power is equal to the force, which is 0.1 times 10 to the minus 3 newtons times 0.02 meters per second. And let's go ahead and bring up our calculator, calculate that out. So it's 0.1 second E minus 3 times 0.02 times 10. I forgot the 10 this time again. And that's 2 times 10 to the minus 5. So let's put the 10 in here just to make it for record purposes that I did it right. Okay, so that's 2 times 10 to the minus 5 watts. So not very much power. But then again, how much power do you need if you're a fly to climb a wall? Okay, let's see what's next. It's your free response. Good luck. We'll see you next time.